Hello. This lesson has been prepared by Jorge Olivar, forest engineer and expert in forest inventories, Luis Pesquet, PhD in geography and expert in spatial analysis and geostatistics applied to remote sensing and land cover dynamics, and Joan Pino, PhD in ecology and expert in landscape ecology, spatial analysis, and GIS applied to urban forest ecology. The lesson will approach us to some GIS and remote sensing tools of great interest for urban foresters. Let us then introduce the fundamentals of GIS and the raster model. A geographic information system, GIS, is a computer system prepared for capturing, storing, checking, and displaying spatial data at diverse scales. GIS can overlap and combine many kinds of data sharing the same cartographic reference system defined by a geographic projection, for example UTM, and a datum, including a geoide or terrestrial model. GIS helps us to understand spatial patterns, relationships, and context, and to improve management and decision-making in biodiversity and ecosystem management and land use planning. GIS has converged to the general structure of information systems, including database management systems, languages, objects, and services. As a result, GIS software has become a kind of client software specialized in obtaining the information from servers of data, maps, and geoservices. Information available in these geoservers follows international standards that allow their interoperability among servers and clients. There is an example of this GIS servers in the Catalan Data Cube, which is an open source geospatial data server that helps you harness the power of satellite data. Let's see the raster model. The raster data model is a widely used method of storing geographic data, and it is the most common in GIS servers. It most commonly takes the form of a grid-like structure that holds values at regularly spaced intervals over its extent. Rasters are especially well suited for storing continuous data such as temperature and elevation, but they also are useful for discrete and categorical data such as land use and land cover data. Extent and resolution are the main factors defining raster properties. The first corresponds to area delimited by minimal and maximal coordinates. Resolution refers to raster definition in many respects. Spatial resolution corresponds to pixel size. High or fine resolution rasters have comparatively closer spacing and more gray cells than low or coarse resolution rasters. Thematic resolution refers to the number of different values that can be represented in a pixel. This depends on the amount of information, that is, bytes, deserved to each pixel. Other definitions of resolution are strictly applied to satellite images. Temporal resolution corresponds to time interval between two consecutive images covering the same area in the Earth's surface. Spectral resolution corresponds to the total number of bands and spectral range in wavelengths measured by satellite sensors. Now let's see some GIS and remote sensing tools and methods specifically useful for urban forestry. The first are land use and land cover maps, which are categorical maps, often in format raster, resulting from image photo interpretation or satellite image classification. They represent spatial information on different classes or types of physical coverage on the Earth's surface, for example, forests, grasslands, croplands, urban, and other. Land use maps also contain some spatial information on the arrangement, activities, and inputs that people undertake in a certain land cover type to produce, change, or maintain it. High-resolution land cover maps are essential for urban forestry, for example, for assessing the distribution and extent of urban forests and green areas. Another useful method is LIDAR, which is a remote sensing method for determining distance range by targeting an object with an airborne laser and measure the time of the reflected light to return to the receiver. It is commonly used to make digital 3D representation of areas on the Earth's surface and on the ocean bottom by varying the wavelength of light. It has terrestrial, airborne, and mobile application. LIDAR data usually are provided in point data, the named pulses, and summarized into a raster map, for example, of mean values per pixel. They are commonly used to make high-resolution maps with application in surveying, geodesy, geomatics, archaeology, geography, geology, and other. From the perspective of urban forestry, LIDAR provide high-resolution data on forestry height that can be related to essential forestry variables, for example, with forest biomass. There are many different types of LIDAR that could be applied for urban forest inventories. There are airborne LiDAR mounted on top of a plane, helicopter, or drone, in which the light is first emitted towards the ground and then it moves towards the sensor. There are also terrestrial LiDAR installed either on a tripod or on a moving vehicle. In this case, LiDAR collects data points that help in the highly accurate identification of data. It can be either mobile or static. One of the most used raster information in urban forestry are satellite images, which collect quantitative information of light reflectance from the terrain, which is recorded in wavelength bands, for example, infrared or red, by different satellite sensors. Vegetation indices correspond to transformation of two or more bands of satellite images that highlight certain vegetation properties. Essentially, they are based on the high response of vegetation in the near infrared, which contrasts with the low response in red. The most commonly used vegetation indices are NDVI, which is a normalized difference vegetation index, which is the classical vegetation index related with photosynthetic activity. And the second is EVI, the Enhanced Vegetation Index, which is an improved index of photosynthetic activity for high plant biomass densities. Currently, most satellite images are available and free in Internet resources. Large time series of remote sensing images can be visualized and combined in map viewers, many of them with low-load services. For massive processing, some public agencies provide data and information access services, the so-called DIAS, for example, of Copernicus in the European Space Agency. In addition, private initiatives provide processing and cloud computing environments such as Google Earth Engine. Let's see an example of how to assess forest biomass in a metropolitan area using cartographic information, specifically LiDAR and survey data. A highly accurate model of carbon stocks has been developed for the forests of the Barcelona metropolitan area by combining forest surveys with high-resolution LiDAR data processed by the Cartographic and Geographic Institute of Catalonia. Terrain estimates of forest biomass and carbon stocks were obtained from a forest survey with 41 plots distributed by the Barcelona region and geographically located with a GPS. 3 species were recorded and height and normal diameter of all trees over 7 centimeters in diameter were sampled. The carbon stock in each plot was then obtained in 3 steps. First, forest equations were applied to calculate the biomass of each species from the height and normal diameter of each sampled tree over 7.5 centimeters. Second, the carbon stock was obtained by multiplying the biomass value obtained by a species by the corresponding carbon concentration. And finally, the values by the species were added to obtain the total stock per plot expressed in tons of carbon per hectare. Then, a continuous raster with the average values of the LiDAR pulses at 0.5 meter resolution was used as a basic LiDAR information. From this layer, the pixels occupied by wooded areas were selected using a recent land cover map. Linear regression models were then developed by combining the LiDAR and the forest plot data and using the estimated biomass values in the plots as response variables. We considered as explanatory factors several statistical metrics derived from the filtered heights of forests and the fraction of covered data, which is estimated as the percentage of pixels that fall on vegetation relative to the total. Finally, an accurate map of forest biomass was obtained for the metropolitan area of Barcelona, and this map is now used by the regional administration as a support of its policy. Thank you for your attention. We hope that you have enjoyed this presentation and it helps you to grasp the potential role of GIS and remote sensing in urban forestry.